Hi, this is the second presentation addressing the basics of hardware-software co-design. As you already know, these slides follow Patrick Chaumont's book, which is the main title in the recommended literature for this course. After watching this presentation, I expect that you will be able to formulate your own definitions for hardware-software co-design to identify the main design approaches and metrics in this area, and also to explain what is the hardware-software co-design space and how it relates to the dualism between these two design approaches and to the various abstraction levels that they use. You may recall that we finished the previous presentation saying that hardware as well as software can be modeled using RTL programs and C programs respectively. And we should be able to apply this statement to the case shown in this slide, where an 8-bit microcontroller interacts with a coprocessor through a program written in C. And I may start by asking you, can this hardware be modeled as a RTL program? And can this example represent a hardware-software co-design application? Again, please check the book pages indicated on the top right corner for further information. But in this case, what I want you to envisage is that the hardware model must include the microcontroller, its coprocessor, and the interconnections among them, while the software will of course correspond to the program written in C, which will be compiled into 8051 machine code. And before moving on, please consider this exercise. What Xilinx tools would you use to design this system? This brings us to our first definition of hardware-software co-design. And I say first because there may be, of course, various definitions according to what assumptions and objectives you have in mind. In the case of the definition presented in page 11 of the book, we consider hardware-software co-design as the design of cooperating hardware and software components in a single design effort. I believe that it will make sense when you read it, but let me ask you some questions besides the one shown in the slide. What is the meaning of the expression single design effort? How would it apply to the architecture shown in the previous slide? What would you consider poor in this definition? But let's move on to consider the distinguishing features of hardware and software. This is more important than what it may seem at first, because the definitions that we presented earlier become blurred when you consider system-on-chip platforms like those offered by modern FPGAs, where a microprocessor may appear as a soft core, as in the case of the Microblaze CPU that can be implemented in the Basis 3 board, or as a hard-wired core, as in the case of the Zinc platform in the Zibo boards. What I want to call your attention to is that hardware-software co-design requires what is herein called an intimate familiarity with the hardware, or otherwise you will hardly be able to optimize your applications. Please take some time to read through pages 11 and 12 of the book, which address these issues. This brings us to the second hardware-software co-design definition that we will consider: the partitioning and design of an application in terms of fixed and flexible components. What are fixed and flexible components? Compare the two definitions that were presented and comment upon what distinguishes one from the other. Do you consider one of them preferable to the other? And again, the same question that was presented earlier. What do you consider poor in this definition? In practical terms, you will see that most designs will consist of writing software, which is of course not a case of hardware-software co-design, but in order to explain why we should move from one paradigm to the other, we need to answer the question shown here. The fact is that most design decisions result from a trade-off between cost and benefit, and this trade-off is deeply influenced by technological and economical reasons. Cost is mostly associated with design time, and benefit is frequently associated with performance in the form of speed. This graph compares the software and hardware implementations with respect to speed, and you may find it interesting to check what is said with this respect in page 14. In what it comes to energy, our metrics may be based on efficiency or consumption, depending on whether we want to think about performance or cost. One way or the other, going for a software or a hardware implementation will lead to different results. So we need to consider a range of driving factors when making decisions. This slide summarizes the main driving factors in hardware-software co-design. I don't want to read and discuss each factor individually here, since it will be better for you to go through what is said in pages 15 and 16. You can pause the video here and take a few minutes to read these two pages. The driving factors that were listed in the previous slide influence the platform selection process according to the hardware-software co-design space illustrated in this representation, which brings into evidence a few interesting and important aspects. On one hand, what we generally call hardware and software will have quite different meanings according to the selected platform. Software moves away from pure C, C++ code as we go from the left to the right. On the other hand, flexibility evolves in the opposite direction, since modifications are relatively easy to accommodate at the far left, but cannot be accommodated at all once an ASIC has been manufactured. Please read through pages 17 to 19 and reflect upon what the author says there regarding this co-design space. Each platform represented in the previous slide corresponds to a different trade-off between flexibility and efficiency, and the two most important questions challenging the work of designers are: what is the best platform for a given specification? And how can we map an application to a given platform? The simple example code shown here can be used to illustrate these challenges. It carries out a dot product calculation, and it might be used directly into the leftmost platform shown earlier as C code running in a RISC platform. This may be the most straightforward solution, but it isn't surely the one offering the best performance, since a digital signal processor with two multiply accumulate units would be able to calculate two loop interactions simultaneously and therefore significantly reduce the computation time. And we might still ask ourselves what additional performance could be obtained by moving farther to the right in the co-design space. This reflection brings us to what may be called the dualism between hardware and software design, since these two design approaches lead to very different results in these 6 areas. I recommend you to pause the video for a moment and try to explain the reasons that lead to these differences. In this last slide, I would like you to reflect upon the various abstraction levels that can be used. Notice that the abstraction level grows from top to bottom, and that not all of them are equally important for hardware-software co-design. What levels would you consider most important for this purpose? And that's all. Thanks for your attention.